Now that we have connected the derivative with its graph, we also want to look at what this really does mean out in the world and how we can use it to help us make decisions. A couple key words that we need to connect to optimization or to optimize are certainly the words maximum or minimum. If we are trying to make the most money that we can, then we're trying to maximize our profit, or we might be trying to minimize our cost. We may also remember want to be looking at our marginal items, like our marginal cost, our marginal revenue, and our marginal profit, and see if we can't make our marginal cost as low as possible, but make our marginal profit as high as possible. And all of these, if you remember, are tied into the first derivative. And so the first derivative gives us a lot of information about what companies and things should do. So as we start to our discussion on optimization, keep remembering the connection to those critical points in the first derivative. So again, our goal when we want to optimize something is either to make it a maximum or a minimal amount, and it depends on whether it's a good thing or a bad thing. There are basically 6 steps you want to go through every time. If there's a picture to be drawn, we definitely want to draw it just to help us visualize what's going on. We write the function for whatever we're trying to maximize or minimize. So if I ask you what is the maximum area, then we are going to write the area formula, because then when I take the first derivative of the area formula, I can find out what the maximum point is for the area. We're going to graph it to help us visualize what's going on, and we're also going to try to make sense. For example, if we're talking about how many trucks we should build to maximize our profit, and one of our answers is negative, then we're not going to use that negative answer, because in the real world you can't make a negative number of trucks. We're also going to make sure to find the critical points, which is where our first derivative is 0, or if our first derivative does not exist. And then in the end, we put all that together and we select the critical point and the correct answer, and we make a statement to the effect. Now, this first example has absolutely nothing to do with the real world. I just wanted to give us a very simple one where you can see that all the different components. Sometimes you have to use 2 equations, what I call the primary equation, and then if we need helper equations. Now the primary equation is easy. It's whatever you are maximizing or minimizing. That's going to be your primary. So in this case, it says we have 2 numbers. So let's call our 2 numbers A and B. And it tells us the sum of those 2 numbers is 20, but it wants us to maximize the product. So we then, whatever we're trying to make the biggest or the smallest, is what our primary equation is. So we're going to maximize our product. So we're going to write an equation for the product, and that is going to be our primary. And we're going to put it in terms of, you can do it in terms of A and B or X and Y, but our product function, let's make it based on A. I could have picked B. Well, I could do implicit differentiation, but the problem here is I've got this function over here on the left. I don't even have a number, and then I have A times B. That's where the helper equation comes in. We happen to know that the sum of these 2 numbers is 20. And therefore we could solve for B, and we could get 20 minus A is the same as B. We can take that helper equation and plug it in over here so that everything we have is in terms of A. If I had picked I wanted it in terms of B, then I would have solved for B. So the helper equation is used when you have more than one variable over in your primary. So now if I distribute this, I get 20a minus a squared. Now that is my actual function. If I wanted to know what my maximum was, I need to figure out where this product is the largest, which means I need to find its critical point. To find its critical point, I have to first take the derivative. When I take the derivative, I get 20 minus 2a. My critical point is where my derivative is either 0 or undefined. Since I don't have any fractions or anything, I'm not undefined. I solve this for a, and I get a is 10. So at a is 10, and let me draw a little thing here. At a equals 10, we have a critical point. And the question is that critical point a maximum or minimum? So now we find our second derivative, which is just -2. It doesn't even matter where we're looking at on our function. The second derivative is always -2, which means that it is always concave down, which means that at a equals 10, and so if a is 10 and they add up to 20, that actually means b is 10. We have a maximum product. So the largest number that if the two numbers add up to 20, the largest product that you can get out of that is 100, because it would be the 10 for A and 10 for B. So let me kind of recap what we did. Number one, let me get a red pen here. Number one, we set up our primary and then our helper equations. We picked our primary because it's what we wanted it to be maximized or minimized. We found the first derivative and set it equal to 0 so that we could find the critical point. Once we found the critical point, we tested it in the second derivative, and we found that this one is always concave down, and so therefore it is a maximum, which is what we were looking for. The A value was 10. I plugged that in to the original product equation, and I got I plugged it in to the A plus B equals 20, which gave me another 10, and that would be my maximum product of 100. So our answer is, if your two numbers are 10 and 10, that gives you the largest product possible if the two numbers have to add up to 20. All right, let's go to the next example. And so this one is the perimeter of a rectangle is 8 square feet. It should not be square. The perimeter of the rectangle is 8 feet. Find the maximum area of this rectangle. So we have a rectangle, and we know the perimeter equals 8 feet, but we don't know what the area is. So let's call this our width and this our length. Our primary equation is what we are trying to maximize. We are maximizing the area, and so our equation will be area equals LW. Now we have to pick an equation or we have to pick a variable for which we're in respect to. So let's pick L, which means we only want L's on the right side. I'm going to get the same exact answers if I had gotten W's, all W's, so A of W. Now, I have an L and a W on the right side, which gives me a hint that I need to go look for a helper equation. The helper equation has to do with the fact that the perimeter is 8. So remember that perimeter is 2L plus 2W equals 8. We want to solve for W, so it's in terms of L. So W equals 8 minus 2L over 2. We can clean that up one more step, and we get 4 minus L. So back in the primary equation, in place of the W, we're going to put 4 minus L. And if we clean that up, we get 4L minus L squared. We want to maximize the area, so we first find the first derivative, which is 4 minus 2L. To find the critical point, we set it equal to 0, and we get L equals 2. And now to find if it's a max or min, we take the second derivative, which is negative 2, just coincidence compared to the last one, and so that means that we are concave down. And if you look at your graph of this function right here, if you were to put that box in your calculator, you'd get a concave down parabola, which means at length is 2, we're going to get a maximum. So if I redraw my rectangle, I know the lengths of these have to be 2. I know my perimeter is 8, and so what that actually tells me is that my width also has to be 2. So in fact, a square that is 2 by 2 is going to give us the maximum area of what? Well, the length would be 2 feet. The width would be 2 feet. The maximum area would be 4 square feet. Because it is concave down. If I were a person putting in dog fences, those underground wire dog fences, and somebody bought 8 feet of wire and they wanted me to give their dog the maximum area I could for them to play, the maximum area would be a yard that is 2 feet by 2 feet. And maybe it's a really small dog. Now let's do an example that the answer's not 2 feet by 2 feet or 10 by 10 or the same answer, because that's just coincidental. So now we have a rectangle or a fenced-in area, but it's along a river. And so we have little pigs in this river, and pigs don't like to, or they're not in the river. They are, I think that looks like a chicken. I better put some ears on it here. I gotta put a little tail. There we go. We got ourselves a pig. The pigs are by the river, which I'm sure that the environmental people would not be happy about. Pigs don't like to swim, so you don't need to put fence along there. Okay, so you just need to enclose 3 sides of the rectangle. And we have purchased 800 meters of wire, but now it's not for all 4 sides. So first let's label our diagram. If we call this our width, and then this would be our length, for this rectangle we're only going to have 1 length. Now we do want to maximize our area, so our primary will still be about area, and it will still be L times W. This time, instead of doing based on L, let's do based on W, just so you can see that it can go either way. I've got 2 variables. To get rid of 2 variables, I have to use a helper. And my helper is that I know I have 800 meters of wire, and I have 2 W's plus 1 L to make that happen. So if I solve this for L in terms of W, I get 800 minus 2W. So my L is 800 minus 2W times the W. which gives us 800w minus 2w squared. A lot of what is done in consulting do end up being quadratics, but not always by any means. And now, getting into a routine here, we find the derivative, which would give me 800 minus 4w. We set it equal to 0. We solve for w, and we get 200. We plug that 200 into here, so L equals 800 minus 2 times 200, or L equals 400. And so if the length equals 400 and the width equals 200, we will have a max area of, let's see, 80,000, and what was it, meters? 80,000 square meters. Okay, so that's the type of concluding statement that you need to make. Alright, now let's get something totally different going. So we have this huge concert that's going up in the Dome football stadium. And 12 minus x squared is the equation of the red dome here. And we're going to hang the projection screen from this point and this point. And so we need to know how long to make it in order to build the largest screen and make it the right size. Alright? Now, in order to do what we do, we pretty much need an x and a y axis. We have 12 minus x squared. Well, what we need to do then is drop our axis, or cut this in half, and use this point right here as our center point. And so we need to figure out then what the value of, or what the area of our screen is, but we need some dimensions on our screen. Well, first of all, if this is our 0, 0, then the distance from here to the little x is actually x units. So that piece is going to be x. Therefore, the piece on the other side is going to be x. So the length of the entire screen is going to be 2x. Now, you did not have to drop your x and y axis in the middle, but it's because it's symmetrical, that was a good idea in order to use the half. Now, we need to know the height of this, and we don't really know the height except that we know this point right here. That point has an x value, whatever it is, because we're x units over, and the y value is whatever we get when we plug that x into f of x. So the address of this point, once we know our x, we can plug it in to 12 minus x squared. So the height of that screen has to satisfy 12 minus x squared. So we don't have like a 2x there, we have the actual 12 minus x squared gives us our height. Now technically we would plug in a negative x value to get the height, but because x is being squared, that value would become positive anyway. So now that we have the dimensions of our rectangle, we can write an equation regarding the area, which is the length 2x times the width, which is 12 minus x squared. And if we multiply that, we get 24x minus 2x to the third. Take the first derivative to find the critical points, and we get 24 minus 6x squared. If we now set that equal to 0, we get 24 equals 6x squared. We get x squared equals 4. We take the square root of both sides, and x equals plus or minus 2. So what that says is that when you go this way 2 units, or you go this way 2 units, and that gives us a distance that this total screen is 4 units long. Okay. But we also need to find the height of this screen, and to find the height of this screen we have to plug in our x is 2 into the y equals. So y equals 12 minus 2 squared, which is 12 minus 4, which is 8. So the height of the screen is 8. And so now our area, our max area, is 32 units squared, because I don't know what, whether these were yards or feet or whatever. And that's when it is 8 units high and 4 units long. So really the case here is that our screen is not long and narrow, it's more tall and skinny. So that problem's a little bit weird, because to find the y value we had to recognize that the y value of these 2 hook points was the same as the y value for the dome, and we used that to create our maximum area. And one more example has to do with something a little bit different, and that is we have a cylinder, and that cylinder is holding water or something. Okay, so we have ourselves a cylinder, and we know that it holds 1 liter, and 1 liter happens to be 1,000 centimeters cubed. Alright, so the volume of this can holds, the volume of the can holds 1 liter. It's a 1 liter can. Now, it wants us to make that can with the least amount of materials. Companies do this all the time, cereal box companies or anybody in a grocery store. They don't want to lose profits based on the container. So they want it to hold 1,000 units, but they want it to be with the least amount of materials. So this is volume, and we know that the volume is 1,000. The least amount of materials, you need to know that what they're really talking about is surface area, and we want to minimize that surface area. So this one, most likely you found it difficult at first because it looks, like, well, what are they talking about, least amount of materials? You need to know that that represents surface area. So my primary is going to be to minimize the surface area. My helper is going to be that the volume equals 1,000. So to minimize the surface area we need a helper, and in this case it's a volume. So let's start with the helper first. The volume of a cylinder is pi r squared h. So we know that the volume is 1,000, and so that equals pi r squared h. We'll come back to that as soon as we need it. Now, our surface area formula, and if you don't know these, you look them up, but we have 2 circles, one on top and one on bottom, so that's 2 pi r squareds. And then we have the label, that if you peel that label off, it becomes a rectangle, but it is 2 pi r, because that's the distance around the circle, 2 pi r, times the height of the label is going to give you that. So that's how much metal we need for the can. Now, we're going to do our surface area in terms of R to get everything where there's only R's. Now remember that pi is just a number, so you don't even have to worry about that. You treat that like a coefficient. But we come over here, and the reason I chose R, we could have chosen H, but the reason I chose R is because I did not want to come over here and take the square root of R, have to get R by itself. So I picked it to be in terms of R so I could get H by itself because that was easier. So now I go and I plug in that helper equation, and the pi's there cancel and one of the r's cancel. And so what I have is 2 pi r squared plus 2000 r to the negative 1 because that r was in the bottom. Now we take the first derivative. Remember, pi is a number. So 2 times 2 pi is 4 pi and just r. Minus, now we're going to do 2000 times negative 1 is negative 2000 r to the negative 2. Now, where we have a critical point is where that first derivative is 0. So I'm going to do 4 pi r minus 2000 over r squared just to get that positive equals 0. I'm going to move that 2000 to the other side. And now I have to solve for r. So first I'm going to multiply both sides by r. So I get 4 pi r cubed equals 2000. And then I get r cubed equals 2000 divided by 4 is 500 over pi. And I take the cubed, oops, that was a cubed. I take the cubed root of each side, and I get 500 over pi to the 1/3 power, which is the cubed root, which equals approximately 5.42. So this tells me that my radius needs to be approximately 5.42 centimeters. If I plug that in for h, so I have h is equal to 1000 over pi times 5.42 squared equals 10.84. So for my can, I need the radius of it to equal 5.42 centimeters and my height to be 10.84 centimeters in order for it to hold 1000 centimeters cubed. The question now though is the can with radius 5.42 and 10.84 the can that uses the least amount of materials in order to hold 1000? So what we have to do now is ask the question, is it a maximum or a minimum? And to do that, we find the second derivative. So we're finding the second derivative of this statement right here in the red box. And remember, 4 pi is just a number. So the derivative of 4 pi r is just 4 pi. And the derivative of negative 2000 r to the negative 2 would be positive 4000 r to the negative 3. So this would be 4 pi plus 4000 over r cubed. And in place of r cubed, in place of r, we put the radius, so we're going to do the double derivative of 5.42. And so we do 4000 over 5.42 cubed. And honestly, it doesn't matter what our answer is. We're just trying to find out if this is a max or min. This entire value, everything in it's positive, and therefore the second derivative says that we're concave up, which means we have a minimum value. So the second derivative is always going to prove that what you have is either a maximum or a minimum. So as you go through these problems, making sure to identify your primary equation and your helper equation, draw pictures, look at graphs, and make sure to make that conclusion at the end, what your result is and what is the maximum or minimum that it gives you.